All right, here's Mr. Koker back doing installment number 2 of the notes for April 8th. These are our eclipse notes since we're doing remote learning during the eclipse. So this is installment number 2 for April 8th, 2024. So we've been talking about galvanic cells. So part of the skill of figuring out these galvanic cells is being able to an example of a galvanic cell. So I'm going to give you some parameters and then we'll think about what that galvanic cell might look like. So one of our two half cells, remember a galvanic cell always has a left and a right. One of our two half cells is going to be a metal silver electrode with a 1 molar silver plus 1 ion in solution. The other one will be a copper metal electrode, which has 1 molar copper plus 2 ion in solution. Of course, we would always have some negative ion with the silver, something like silver nitrate, and with the copper, copper nitrate, copper 2 nitrate. So the nitrate's a spectator ion, not important. The important reaction is silver plus 1 and silver, and copper plus 2 and copper. So we pretty much have an idea of what the two half cells might look like, and of course we would connect the silver metal electrode and the copper metal electrode with a wire, and we would also have silver plus 1 on the side with the silver electrode and copper plus 2 on the side with the copper electrode, and some kind of porous disc or salt bridge to connect them up. So that kind of gives us an idea of what the picture is beginning to look like. But this wants us to include in the sketch the potential of the cell, the direction of the electron flow, and also labels on the anode and the cathode. So to do that, we will need to know which one is going to be the reduction reaction, which one will be the cathode, which one will be the oxidation reaction, which will be the anode, red cat and ox. And we would need from that standard reduction potential table what the E0 of each half cell is, what the standard reduction potential for each cell is. So if I go back to one of those standard reduction potential tables, and I scan through here, I see as the second one Ag2 plus. That's not what I want. I want Ag plus and Ag. And I find that about 3/4 of the way down the first column. Ag plus plus electron yields Ag with a 0.80 volt standard reduction potential. I keep scanning. I see copper plus 1. That's not what I want. I want copper plus 2 and copper. I find that in the second row of the right-hand column. Copper plus 2 electrons yields copper 0.34 volts. So, gauging the position of these two, the silver ion is the 0.80 volts. The copper plus 2 is the 0.34 volts. So, being lower on the table, the copper plus 2 is going to be the one to flip and be the oxidation step. So we're going to run the Ag plus electron yields Ag. We'll actually run it twice so we can get 2 electrons. But that doesn't affect the E0. The E0 stays at 0.80 volts. That's going to run forward. That's going to be our cathode because that is a reduction, red cat. And then the copper plus 2 electrons yields copper. We're going to run that in reverse. The copper is going to convert to copper plus 2 and lose 2 electrons and be the oxidation step, so that will be our anode. So our cathode is going to be the silver side. The anode will be the copper side. The silver ions will turn to silver metal, so the silver electrode will get additional atoms added to it over time. The copper side is going to turn into copper plus 2, so the copper electrode will slowly dissolve into solution as copper plus 2, lose mass, while the silver side gains mass. Now, that identifies our anode and cathode. The silver will be the cathode, the copper will be the anode, because that's where reduction and oxidation are occurring. And what will be our voltage? Well, it's the E0 cathode minus E0 anode, or it's 0.80 volts minus 0.34 volts. And that comes out to 0.46 volts. Now, which way will the electrons flow? The electrons flow from A to C, from anode to cathode. So that means the copper side is going to be producing electrons, which will flow through the wire to the cathode side, which is the silver reduction side, and then electrons will flow through the wire from copper side to silver side, and then to balance the charges between the two sides, there will be allowable electron flow or ion flow through the salt bridge or the porous disk. So that's what I'm picturing as my galvanic cell. And here's what it would look like. So my copper side is my anode, my silver side is my cathode. Electrons are flowing from the copper anode to the silver cathode. Ions are flowing in and out of the salt bridge to help further keep the two beakers equal charge, so you don't get something trying to oppose the flow of electrons. And on the anode side, we see copper atoms coming off into solution as copper plus 2. On the silver side, we see silver ions going on as silver. Since reduction is occurring at the silver side, then you need to be flowing electrons over there, because reduction requires electrons. And so we'll be flowing electrons from the anode to the cathode, from negative to positive. And the voltmeter reads the proper voltage, 0.46 volts. So we've answered the question about sketching the cell and what would be the potential, what would be the direction of electron flow, and the labels on the anode and cathode. The only thing that this picture I found on the internet didn't include was that the electron flow would be from left to right. Okay, trying another example. Let's try one with a zinc electrode with zinc ion and a copper electrode with copper ion. So in this case, I need to decide which one's going to be the cathode, which one's going to be the anode, what the voltage is going to be, and the direction of electron flow. So, looking for, well, I already know where the copper plus 2 is. I just used that one with the silver. That's in the second row of the, up there at 0.34 volts on the second row of the second column. But then looking further down that column, I find the zinc at negative 0.76 volts. So whereas previously the silver was first in the number line and then later was the copper, this time copper is ahead of zinc on the number line. The copper is at 0.34 volts, the zinc is down at negative 0.76 volts. So that means this time the copper reaction gets to be the reduction step because it's higher on the number line on the standard reduction potential table. It's 0.34 volts. So the copper plus 2 will add 2 electrons to become copper. That will be the cathode side. That's where electrons will flow to. And the zinc reaction will have to flip, and zinc atoms will become zinc ions, zinc plus 2 ions, and lose 2 electrons. So that will be the anode, because that is oxidation. The copper side will be the cathode, where reduction occurs. and the electrons should flow from the anode to the cathode, from the zinc side to the copper side. So that would look something like this. So we see oxidation occurring with the zinc, because we flipped the zinc reaction because it was lower on the chart. We see reduction occurring with the cathode copper. So the electrons being added to copper plus 2 to form copper atoms, and the addition of copper atoms to the copper electrode. The copper electrode would slowly gain mass as it adds atoms. The zinc electrode slowly loses mass as it loses zinc atoms, forming zinc ions. So the zinc side is the anode, the copper side is the cathode. Electrons are going to flow from anode to cathode, first left to right again. And the voltage, what's the voltage going to be? 1.10 volts. Why? This is a mistake here that it's listed as negative 1.1. It'd be 1.10 because 1.10 is 0.34 minus negative 0.76. Positive voltage always means spontaneous reaction. Okay. Again, describe a galvanic cell. Here we have silver ion and silver metal, and then iron plus 3 and iron plus 2. So we go back to our table. Those are found at 0.80 volts for the silver and silver ion, and then 0.77 volts for the iron plus 3 and iron plus 2. Now we have a piece of silver metal, silver, Ag. That's going to be your electrode. Silver ion is going to be in solution. 0.80 is above 0.77 on the number line, so silver gets to be the reduction. Silver gets to be the cathode. The iron reaction gets to be the anode, because we will flip it and run it as oxidation. Both have one electron, so each reaction runs once per once of the other reaction. And our voltage is 0.80 volts, E naught of the cathode, minus 0.77 volts, E naught of the anode, or 0.03 volts. Now in this particular case, because iron plus 3 and iron plus 2, neither one is a neutral metal atom, we do not have a piece of metal or solid that we can use for an electrode amongst the two ions, so we would have to use an inert or chemically stable electrode like a strip of platinum metal. So platinum might be our inert electrode. Now to be under standard conditions, the silver, the iron 3, the iron 2, those would all be at 1 molar, and the temperature would be 25 Celsius. The silver would be a piece of solid. So, describing completely the galvanic cell. The silver is the cathode, the iron is the anode, because it's the one that flips because it's slower. Reductions occurring at the cathode, oxidation at the anode, and anox, red cat. The voltage would be 0.03 volts, 0.80 minus 0.77. They're 0.03 apart on the number line. And the iron would have a platinum electrode. The silver side would have a silver electrode. So electrons would flow from anode to cathode, so electrons would flow from the iron side to the silver side. And of course we would have some kind of porous disk or salt bridge. So here's some slides describing that. Silver gets to be the cathode, iron gets to be the anode. So your cell reaction would be Ag plus Fe plus 2 makes Fe plus 3 plus Ag. E naught 0.80 minus 0.77, 0.03 volts. Silver is going to receive electrons in order to be the reduction cathode. So iron is going to lose electrons to be the oxidation anode. So electrons will flow from the compartment that has iron to the compartment that has silver. Oxidation occurs in the silver side, so it functions as the anode. Reduction occurs on the silver side, so it functions as the cathode. So the electrode with the silver cathode and the silver +1 ion, the silver is going to be the electrode. The other side, because there is no piece of metal, these are both ions, Fe+2 and Fe+3. Piece of platinum would have to be your electrode. And of course we would have appropriate counter ions such as sulfate or nitrate or something to balance out the silver and iron ions charges. So your line notation might look like this. Electrode for the anode, Pt solid, piece of platinum. Line, the solid is a different phase than the ions, but we would list both ions, and if this is a standard cell, we might list them as 1 molar. The double bars mean a salt bridge or porous disk, followed by silver ion and silver metal as the components of the cathode side. So A to C, alphabetical order. And that's also the direction of electron flows from left to right in this case. Might look like this. This one's using a porous disk instead of a salt bridge, but that also gets the job done. All the ions 1 molar. Use a piece of platinum for the anode side, piece of silver for the cathode side. Electrons would flow and you'd have a voltage, which is not a very healthy voltage at all, just a very minimal voltage of 0.03 volts. Okay, so that finishes us up on the idea of galvanic cells. So by now you hopefully understand that if you're in lab and you have some beakers and you have capability of connecting those beakers with salt bridge or porous disk, and you have the right solutions, you have the right pieces of metal, you can set it up properly according to standard states and standard concentrations and pressures and whatever, that you can use that chart to actually determine what you can expect the voltage to be between 2 half cells, and which one's going to run in the reduction direction, which one's going to run the oxidation direction, which one you're going to call the cathode, which one you're going to call the anode, and what the voltage is going to be between those, or what is the cell potential. So now, extending that idea of cell potential, or the voltage of your cell, we then ask, how does that convert to the amount of work that can be done by that battery? How big of an electric vehicle can that battery push down the road? And what is the free energy, the amount of energy that you could actually, amount of maximum work, free energy, that you could harvest from that much cell potential? So a little bit of physics here. Work is accomplished because the electrons going through the wire have a thermodynamic driving force. The electrons are able to make things move. The electrons are capable of doing work. They have a thermodynamic tendency, and that tendency can be harnessed to do work. The driving force, which you remember is called the electromotive force, or EMF, that is given a unit of potential difference called volts. And the volts, as we've already said, is the work in joules divided by the charge in coulombs. So it's the amount of work done per charge of electrons or ions transferred between the two beakers. Now, we prefer to define work from this position of the system or the point of view of the system, and so the cell potential E and the work actually should have opposite signs, because a positive cell potential will create a battery that will do work. Remember, doing work is negative work by the system. And so actually what we should define here is E equals negative work, joules, over charge, and we'll use the letter Q to stand for charge. Now if we rearrange this equation, we can also write it as negative work equals the amount of charge transferred as the battery runs times the voltage or the electromotive force or the E naught or E of the cell. Now this is the maximum work. This is assuming no loss of heat, no loss of any, that all the work gets harnessed to push things down the road or move things around or whatever that you're. And remember, we learned back in thermodynamics that you never get 100% of the work out of something. But this is what is the ideal maximum amount of work you could expect a battery or a galvanic cell like this to generate. And the amount of maximum work is negative QE. Work is never the maximum possible. If you got current flowing, you're probably going to have some heat generated. You're going to have some resistance in the wire. It's going to heat up. You're going to lose some of your energy along the way. In any real spontaneous process, some energy is always wasted. I mean, it's that third law of thermodynamics. You just can't even break even. Actual work realized is always less than the maximum calculated work, but we should still be interested in what is the upper limit on how much work I could expect this particular battery to produce. So E is the potential difference. So that's the voltage. Q is how many coulombs are being transferred, how many coulombs of electric charge are being transferred. Now, to relate coulombs to an amount of electrons that we can comfortably use for chemists. So instead of counting electrons individually, because there's so many of them, we like to count them in groups of 6.02 times 10 to the 23rd, or moles of electrons. So when the physicists figure out what the chemists are thinking, when they come to one mind, what they end up realizing is that it takes 96,485 coulombs of electric charge, as measured by physicists, to be a mole, or 6.02 times 10 to the 23rd electrons. So the unit of charge used in physics is the coulombs. The chemist counts things as moles. And so 96,485 coulombs for physicists is the same as a mole of electrons for chemists. So Q, the amount of charge, is actually the number of moles times 96,485. So if, let's say you had 1.33 moles of electrons, then you would multiply that by 96,485 coulombs per mole to get converted to coulombs. Because remember, volts is joules per coulomb. Now this number, 96,485, shows up in a lot of calculations, enough that it actually has a name. Just like 6.02 times 10 to the 23rd is called a mole, 96,485 coulombs is called a Faraday. Michael Faraday, famous chemist and physicist that worked with electricity. So 96,485 Faradays is a mole of electrons, or actually 96,485 coulombs is called a Faraday, which is also a mole of electrons. I said it better the second time. Ignore what I said the first time. So remember, the maximum work is actually delta G. So now we're tying it into previous chapter on thermodynamics. Maximum work equals delta G. So maximum work is negative QE, charge times voltage. Voltage is joules per coulomb, Q is coulombs. So the maximum work is negative QE, or delta G, and then Q is NF, so put it all together, we get, if you want to know the change in free energy for a given redox reaction, a pair of redox reactions, reduction and oxidation reaction paired up, then it's going to be negative NFE, where N is the number of electrons, or number of moles of electrons. F is Faraday's constant, 96,485 coulombs per mole, and E is the voltage. Now, if you look at this, a negative delta G is considered spontaneous, and a positive E is also considered spontaneous. So delta G equals negative NFE is an important equation. And of course, if you're doing your reactions with standard conditions, 25 Celsius and 1 molar and 1 atmosphere and all that, then delta G naught is going to equal negative NFE naught. Got the little O signs up there. So your maximum cell potential, E naught, is directly related to the free energy. A positive E means a negative delta G, meaning you have a spontaneous redox reaction that can be made into a battery that can do work, because you're harnessing the thermodynamic favorability of the reaction to create a scenario where you are able to get energy out of the process. Which gives us a way to find delta G. For redox reactions, you can actually make these batteries measure the voltage and solve for the change in free energy. And that's one way to get the delta G. In fact, we've learned a lot of ways recently about how to find delta G. This is an experimental means using the voltage of a galvanic cell. If you set it up under standard conditions, you can find delta G naught. So this is a confirmation. A positive E for a galvanic cell, where you take a higher number minus a lower number from that standard reduction potential table, means a negative delta G, because the way the formula works, negative delta G will give a positive E naught. So this is always a combination that you can always put together. A positive E corresponds to a negative delta G. And that means the reaction is spontaneous, meaning it's thermodynamically favorable, meaning it can be harnessed to do work. The type of work will be electrical work. We're going to use the chemical energy to convert to electricity, and then use the electricity, the voltage, to power something, make something happen, work. So a math problem might be, I've got a redox reaction. Let's see if we can use the standard reduction potential table to calculate the delta G of this reaction, and then determine, is it spontaneous or not. So I have a reaction. I've got some copper 2 ion and some iron atom, and it's forming copper and iron plus 2. So I see in this reaction that the copper plus 2 is being reduced, the iron is being oxidized. Plus 2 to 0 is reduction, neutral to plus 2 is oxidation for the iron. So that means on the table I want to look up the copper plus 2 reaction and the iron plus 2 to iron reaction. So here's my table. Copper plus 2, I've used that one before. I know it's the second one on the right column, 0.34 volts. And now I'm scanning for Fe plus 2 and Fe. And I find it. I find it down at negative 0.44 volts, about the middle of the second, halfway down on the second right-hand column. Fe plus 2 electrons yields Fe. So that means I want to run it in reverse, Fe to Fe plus 2. I want to run the copper forward as a reduction. Copper plus 2 yields copper. So let's see if that was what we did. Copper plus 2 yields copper. Fe yields Fe plus 2. So that's right. So we already can guess this reaction is spontaneous because the proper one of the two reactions has been reversed. The iron has been reversed, the copper is running forward. Now, to further do the math, to get the delta G, I want to know what the E naught of the cell is. I want to know what the voltage of the cell is. So looking at the number line, the copper reaction was at 0.34. The iron reaction is at negative 0.44. So E naught of cathode minus E naught of anode, 0.34 minus negative 0.44. Actually, because one's negative and I'm subtracting it, I'm adding it. So subtract a negative means to add 0.34 plus 0.44, so 0.78 volts. So then, using 0.78 volts, so here's a slide that kind of goes over what I just talked about the voltage. Copper's running forward, cathode 0.34 volts, iron runs in reverse, anode negative 0.44 volts, or negative E naught, and so E cathode minus E anode comes out to 0.78 volts. Now that can plug into the delta G equation to find the delta G of the reaction. Delta G equals negative NFE. Now N is the number of moles of electrons. Now if the copper is going to go from plus 2 to neutral, the iron's neutral to plus 2, that's 2 moles of electrons being transferred. Since 2 electrons are transferred per atom, 2 moles are required per mole of atoms. Moles of iron and moles of copper. So I'm going to use 2 for the N. I'm going to use 96,485 for the Faraday constant F, and 0.78 joules per coulomb, or 0.78 volts, for the E naught. Multiplying these together, I get 1.5 times 10 to the 5th. Canceling units, moles, electrons cancels, coulombs cancel. I see that my final unit for the delta G is joules, negative 1.5 times 10 to the 5th joules, or negative 1.5 times 10 to the 2nd kilojoules. But either way, delta G is negative, meaning spontaneous, meaning this reaction is written in the proper direction, the copper being reduced and the iron being oxidized. Remember, positive E naught of cell means negative delta G, means thermodynamically favorable. This reaction could be harnessed. We could make one of those cells with the 2 beakers and the salt bridge and all that and put it together with copper and iron and the proper molarities. We could get a voltage, we can run that voltage, we can make an electric motor go around, or whatever else we want to do with the electricity. So we realize now the process is spontaneous because it's got both a negative delta G and it's got a positive E naught. And those two always go together. This reaction has actually got its usefulness. It's used industrially to deposit copper metal from solutions where you dissolve the copper ore. The copper ore becomes copper plus 2. Use iron metal and you're going to get the copper metal to come out of solution. Okay, so let's see. Use the data from table 17.1, again, the standard reduction potential table, and predict whether 1 molar nitric acid can dissolve gold to form gold plus 3 1 molar. Let's think about that. What would that reaction look like? Okay, I see what I want. HNO3 is H plus NO3 minus because it is an acid that is a strong acid. So I'm scanning through this chart and I'm finding I'm seeing some stuff with H plus. Is there anything that includes NO3 minus? H plus and NO3 minus. I found it. 0.96 volts, about 3/4 down on the left side. NO3 minus plus 4H plus 3 electrons yields NO gas plus 2 waters. Okay. Now, what else did I want? I wanted to be able to get AU3 plus from AU. Well, that's actually oxidation, so that means it would have to be below this one. But when I find it on the chart, it's actually at 1.50 volts. AU3 plus 3 electrons yields AU. So they are in the wrong orientation. The AU plus 3 yields plus 3 electrons yields AU should be the one running forward, not in reverse, because 1.5 is above 0.96. So that means that this reaction is not spontaneous, which means nitric acid should not be capable of dissolving silver metal. So here's our 2 half reactions. NO3 minus and 4H plus make NO and water and use up 3 electrons, so that should be the cathode, 0.96 volts. And then the anode should be AU yields AU3 plus 3 electrons, negative 1.5 volts. Because we're running it in reverse, we change the sign, but when we add 0.96 to negative 1.5, we actually get E naught of the cell to be negative 0.54. If E naught is negative, that means delta G will be positive. So since E naught is negative, the process will not occur under standard conditions because it's not thermodynamically favorable. The gold won't dissolve in 1 molar nitric acid. However, just as an aside, you are capable of dissolving gold, but it needs to not be 1 molar nitric acid. It actually needs to be a 1:3 mixture by volume of concentrated nitric acid and concentrated hydrochloric acid. That's the mixture of acid that can actually dissolve gold metal and make it into ions. Since it's capable of dissolving gold, it's actually been given the name, that mixture of nitric and hydrochloric acid is called aqua regia, which in the Latin means royal water. This is a solution capable of dissolving gold, royal water. Okay, I think I'm going to call that a day. I'm going to say that we have accomplished enough for the day of the eclipse, and we'll pick up at 17.5 on Tuesday. So expect a quiz, expect a lab. I'll try to figure that out between now and Tuesday. And enjoy the eclipse. But I'm going to call this the end of the 2nd installment, and these 2 installments will be all that I will say we'll cover for today for remote learning. Feel free to go back and rewind and rewatch or fast forward through any of this as you need to learn it the best possible. But we will consider 17.5 section to be the start of the next set of notes. I'm going to put this direction in the announcement for this, but I would appreciate if for each of these videos, if you will put a comment at the bottom letting you know that you have been able to access the video. If you just want to put the comment here, meaning I'm here, I got to the video, I made it work. That will let me know that the videos did upload on YouTube properly and that they are visible by you guys and you guys are able to complete your lesson for today. So a little bit less than 2 hours and 45 minutes, but I think we got enough in. There's a lot to digest here. Take your time, go back, ask me questions, send me emails if you want to. Come in before class on Tuesday. But this is the end of what you're responsible for up to the end of the day on April 8th. So I'm going to sign out and see you guys in class on Tuesday.